Professor Martin Jarrett, who is transforming the world of Constellium into low-carbon Constellium. And you're just going to explain how you're doing that, I believe.
I'll give it a go. Okay, so so my name is Martin Jarrett. What I'm going to talk about today really is specifically what we're doing with Professor Fan and his team in BCAST and how that actually relates to aluminium in the automotive area. So I think the first thing, just the agenda. So I'm going to do a very quick overview of the automotive extrusion market in both Europe and North America, the target components that we're looking at, the technical capabilities that we've now developed to prove those technologies. I'm going to focus in on two specific areas. One is the crash management system, particularly the front end, and the other, no surprise, is the battery box. I'll then highlight, I think Fan has mentioned it already, the STEP program. I'll then talk about CirCanal, which stands for Circular and Constant Aluminium. Obviously that's about recycling. That wasn't mine. That was Jeff who came up with that idea, so thanks Jeff for that title. Also, really important to us is the people pipeline. Today it's becoming increasingly more difficult to recruit the right sort of people into the company. And it's vital that we've got people working on the right things in good universities that we can bring into the company. So that's really important to us. And then a quick summary at the end. So where are we then? So from an aluminium extrusion point of view, so Mark's done an eloquent job talking about aluminium. I'm now diving down into just extrusion. So in 2022, we've got a market around about 330,000 tonnes. By 2030, that market doubles. And of the three component areas that we're specifically focused on, we produce structural aluminium extrusions for crash management systems, side sills and battery boxes. That market is growing faster. That goes up 3 times in the next 8 years, basically up to around about 450,000 tonnes. That's a big growth area in our market. And we see exactly the same thing in North America. And that is driven by electrification. So, how do we address that? Well, we're looking at, in this particular case, 4 specific programs. We're looking at high strength HS, high strength aluminium alloys. We're looking at HC, so that's high crush performance. So in a crash situation, we need to absorb the energy. So we have a portfolio of alloys. We've got our STEP program, which I'll go through. We've got a LiVE, which is basically for aluminium enclosures in vehicles. And we've got CirCanal, which actually uses high levels of post-consumer scrap, and we're targeting less than 2 tonnes of CO2 per tonne of aluminium. Basically, we're aiming at less than that, around about 1. And if you see here, if I can get this thing to work, well, I'll just point to it. Side sills now, in electric vehicles in particular, are very highly complex multi-cell extrusions. And they need to be to absorb the energy of the side impact to protect the batteries. So the technical capabilities that we've now got with the partnership with Brunel, we've got a whole host of designs. So we've got CATIA, LS Dyna. We've got 15 design engineers as part of the team now. We've got the casting and prototyping area. So when we talk about experiments, we do an awful lot of actual hands-on experiments and take that learning into our metallurgical understanding and into our models. And that is vital. Forming and joining, exactly the same thing. We've also got a partnership there with Warwick Manufacturing where we've got laser welding capabilities. We have a rapid prototyping capability in addition to our facilities with Professor Fan in Coventry, with a company called Expert, where we're actually able to make full-size battery enclosures. And obviously we have a full range of testing capabilities because obviously we've got to prove the work that we've done, and we follow a lot of the OEM testing to do that. So, how do we work? Well, we have our capabilities here. So we've got AMPC and AMCC. These are the facilities at Brunel University. We actually marry that with our engineering competency centres worldwide: China, America, and Europe. That's in Germany. Our work is application-led. That doesn't necessarily mean that we're looking at just a product. We're looking at the product, but also the science of how you make it. So that is driving our work programs. So we focus particularly around our alloys. This is just a range of the OEMs that we're working with. I could put many, many more up there, but this is just an example. We actually produce full-size prototypes. What we don't do is produce small pieces of metal for the OEMs to test. We actually produce full-size structures so that we can test them and the OEMs can test them. And that is really important to get some of these alloy variations, particularly when I talk about Circonal, to get those things qualified. We then look at our manufacturing systems. We need to be more efficient of how we manufacture. This is the top row there is more about digital, but we use digital simulations to actually construct and simulate our manufacturing flow paths, because we need to be, as I say, as efficient as possible when we manufacture these parts. And in the STEP program in particular, what we talk about there is something called manufacturing induced properties. So the manufacturing process itself introduces higher mechanical properties into the material. So we don't use separate processes to do that. So, crash management systems, what are we doing? We're obviously looking to optimize the strength. We need to provide design and manufacturing solutions to meet the EV structural performance requirements. And this is really quite interesting, because this is really now pushing the boundaries of the material that we're having to use. To develop the next generation of high strength materials, to prove capability, as I've said, and also to reduce the CO2 content. This is what we've done in the past. We've proven the capabilities for both JLR and BMW in this case, for the Mini. We've actually extruded those materials, and the whole CMS systems in Brunel. We've manufactured those CMS. We've proven that with both those companies, and they are now serial production. So we know the process works. So if we look at what we need to do for crash management systems, we've effectively got three areas. One is the extrusion process itself. Clearly, cost is always going to be a question, so we've got to be able to extrude efficiently. We need to provide high strength, so we need less of it. We obviously use digital twins as well to support our die design. So we've got a whole area of extrusion around what we call productivity. We've then got strategic metal use. Now, what we mean by strategic metal use is recycling. How much post-consumer scrap can we obtain from the market, utilising our material, and drop that CO2 number? And then the final one is the production methods we use. We need agile manufacturing systems. One thing that we've found, particularly when we look at things like battery boxes, although I'm talking about CMS here, is to be able to manufacture components using the same essential manufacturing footprint, but pull in and pull out different machines, so we can actually make different components on the same line. So that's another area we're looking at. And we also look at things like, the welding. Typically, you'd look at, with CMT welding, you're probably looking at a 30 to 40% drop in strength as associated with a heat affected zone. With some of the equipment we've now got with electromagnetic pulse welding, we actually can increase the strength, so we don't get that drop. So how can we then use that in the design of the materials? So This is all part of a program to do that. But just to show you what electrification actually means now to the crash management system. This is the bumper. With an ICE vehicle, we've got an engine in the way. What we had to worry about before was the intrusion of that bumper going into the radiator, which was about that far. Now we have to engineer that material so it actually intrudes around about 0.5 metre, doesn't crack, doesn't move away from the crash boxes, and actually holds together. Because if it doesn't, the car splits in half. So what's happening is as we move to electric vehicles, the materials we use, it's getting even more complicated of how we tailor the manufacturing and microstructures of that material to behave in that way. So it's a really exciting thing. It's really challenging to the industry, and that's one of the reasons we're working with Professor Fan and his team to be able to do that. When we look at battery boxes, we need to understand about battery boxes, and what I mean by that, if we just turn the clock back 3 years, we were talking about fairly substantial structural battery boxes. What is now happening is we're moving those battery boxes into a much more cell to vehicle type structure. That battery box is becoming much more simple, and the batteries themselves are housed in a much simpler box. So in 3 or 4 years, the whole concept of how you make a battery box has changed. So that's part of what we're doing there, to provide solutions for design manufacture, design for performance, to define flexible systems so we can produce different types of battery boxes on the same production line, again to confirm capability, to provide a turnkey solution, and again to drop and reduce our CO2. So I won't go through this in great detail, but this is a typical example. This is a structural battery box. We see structural side intrusion here. We've got the frame itself. We've got cross members. We've got either a sheet or an extruded floor. So when that's placed in a vehicle, that is a structural component of that vehicle. Now what's happening is that these side intrusion beams, these side seals, still critically important, but they're now engineered into the body in white itself, so that the battery box becomes a much simpler structure, and the crash performance, the crash resistance, is taken in the body in white itself. So again, this is a very simple product development cycle. We design, we prototype, we assemble, we have a digital representation of this as well as a physical line. We look at the different joining techniques. We've worked on CMT, laser welding, a whole range of adhesive bonding and mechanical joining. We'll then produce those prototypes, and then we'll test those prototypes, both ourselves and independent testing facilities in the UK. So, what step? Well, Professor Fan obviously borrowed one of my slides. You've seen this one before. So, what this is basically to show the relationship. This is a specific strength relationship, so we've obviously got to divide it through by the density. What this means in terms of step versus these ultra high strength steels. And you can see actually where step is starting to get close to these generation 3 steels. So what we're trying to do is to move that to the right, this way, try and keep the ductility up as far as we can, and you can see why that CMS system. That allows us to use less material, but we've also got to maintain that ductility so that we can keep that crash performance. And we've basically set ourselves two targets. One is how far we can physically take that strength. How high can we go? We currently have HSA 6 with a 370 proof. Now that is a 6,000 alloy, and we've deliberately chosen 6,000 alloys because they're highly tolerant to recycling. So that's one. The other one is we use a slightly softer material, and in this case, how can we still maintain a high level of productivity and then use the step process to increase the strength, perhaps not to the ultimate, but to a higher value. So we have this is part of what we call the Prosperity Grant Program. So we've got a whole host of interactions here. We've got what we're trying to do, where we're aiming for. We look at how we can tolerate insoluble second phase particles with either shear or addition of chemicals. We're looking at the step process itself, which is a combination of precipitates and cold work, so dislocations. We're going down to look at the atomic structure through the atom probe. We're looking at the thermomechanical processing, how that affects the microstructure, and obviously the manufacturing-induced properties. How do we use the cold work of forming, for example, to support the increase in strength? So that's a whole holistic program of work there. And then ultimately, how do we industrialize that? How do we then turn all that into an industrial process and make it? So we're generating an awful lot of information. So Van's already mentioned the ADA process, which is thermomechanical aging, or which is basically what STEP is. We generate a lot of information. A lot of that data then goes into our models. But as I say, a lot of what we do is experimental work, and our teams are generating this information. We then look at how we could then industrialize that, both from an extrusion point of view and from a forming point of view, to be able to capture that information and knowledge. This is fairly simple sort of processes. This is stretching and bending. What can we do with just simple stretching and bending? And because we've got the availability of the electromagnetic pulse forming capability, we can get much higher levels of strain, which we do using this equipment, and potentially that's probably not going to be that useful for a front crash management system, but it could be particularly useful for a rear crash management system, which is a much more simple type structure, and the intrusion at the rear is much, much less. So it's about understanding how we can apply the step process to, in this case, a rear system, and what we need to do for a front system. And what that means in terms of our ability to save weight, if it's highly elastic dominated, then we can effectively we're saving the majority of weight. We can save that's really where the maximum weight saving will come in. When we're into a high crash situation where it's plastically dominated, even though we can get quite significant improvements in strength, ultimately we cannot save that much weight because of the way the material performs in that structure. So that's part of the learning that's coming out of the program, and from our point of view, Constellium's point of view, how do we then take that and apply that to the different components that we manufacture? One interesting thing that we've also learned, and we haven't got an answer to this, by the way, and which is somewhat counterintuitive, is when we apply levels of cold work to, so stretching in this case, to a crush material. So we imagine now in a crush situation, we're crushing that material, so this folds, absorbs the energy. As you increase the composition, as you increase the strength, what tends to happen is the crash index begins to fall, and ultimately, once you get above about 300 megapascals, you start to develop cracks. What we found is when we go through a thermomechanical aging process, the step process, we can actually come off that curve, and what we find is that we can get up to 320 megapascals, and we recover the behaviour. We don't know why yet. It's part of the program we're working on, but it's really quite interesting. So circular and constant aluminium. So what are we trying to do here? So the target is to achieve less than 2 tonnes of CO2 per tonne of aluminium. And just to give you some sort of context of what that means versus the average European number, which is around about 10, over a 10-year period using an 80,000 tonne cast house, that saves 5 million tonnes of CO2. So these are not small numbers. And what we're trying to do is to upcycle aluminium scrap. We need to define the supply chain to do that. We need to prove capability. Obviously, one key aspect of this is that we need to prove this to the OEMs. While the OEMs want to increase the amount of recycling and drop the CO2, what they also want to keep are the chemical compositions they've had for many, many years. You can't have it all ways. And our job is to support them by proving what can be done and what can't be done. So, I'm using this as a context for the UK. This is the situation. Predominantly, we've got our import prime coming in, we manufacture, but look at the UK. We're producing around about, it's nearly 1 million tonnes of scrap in the UK every year. About half of that is exported. We don't use it. Part of it is because we have our own infrastructure in the UK, we can use some of it, but the real issue here is we haven't got an infrastructure to use it anymore. A lot of our extrusion has been hollowed out, a lot of our industry has been hollowed out, so even if we wanted to use it, we can't at the moment because it's going away to predominantly Asia where it can be used. Our challenge is how can we make this material strategic and how can we then establish new industry on the back of that. Now that's not an easy question, it comes down to policy, so investment, etc. But that's a massive opportunity for the UK. So what we're looking at in terms of the circular project, and that's a 10 million pound APC project. Our partners in there are BMW in particular. So BMW are a key partner to that project. So when we're looking at the maximum impurity limits that we can take and produce our materials to, our idea is that we can produce the component parts, we can produce the battery boxes, we can produce the crash management systems and prove capability with the OEMs. So we obviously need to sort the material, and this is just a very simple diagram, whether we go eddy current, X-ray transmission, ultimately LIBS. If we can go to relatively dirty material, there's a cost benefit to that, but obviously that requires more sorting. But what we really need to be doing is to, yes, we understand we have to stay with the compositions we have today, but we need to be moving those compositions to higher impurity tolerant compositions that allows us to use some of these dirtier grades of material. Now that doesn't mean that that material is bad, far from it. It just means that we just need to quantify what the impurity levels need to be. So we have a whole host of tests and processes that we're working through in that program to prove capability to the OEMs. And we'll also produce the gizmo cards with the different compositional limits so that we can take that and use that in the design. And this is just a very quick example. We've got many more actually. But even when we get to relatively high iron levels, I mean, typically in these materials, you're probably talking about 0.2, 0.22. So we're roughly double. We've got relatively high levels of zinc, which is a common impurity. It's really having no difference at all to the mechanical performance and mechanical properties of the material. We've also been able to show, from a corrosion point of view, it's having no difference on corrosion either. And that includes the pre-treatment. And the embodied CO2 in this material, we're now able to also model. We have hundreds and hundreds of compositions from our partners, and we've actually produced, in this case, a digital twin where we can show, obviously depends on the prime. This is a relatively good level, low level of prime. But we can take this down to less than 1 tonne of CO2 per tonne of aluminium with different mixtures of the various grades of scrap. So, I'm nearly there, Jeff. So, the talent pipeline, we have our industrial case program. By the end of this year, we will have 21 active iCase students. Obviously, we've got a very strong presence in Brunel, but we've also got a number of partner universities that we're working with. Obviously, what we're looking at then is our core competence development, which is structural design, digital metallurgy, etc. And what we're doing with those people is obviously we're looking to bring those into the company, into Constellium, but also into the R&D centres with working closely with us. This is an example really of where we've come from. We started in I think it was 2012. We started with one PhD student, going through various programs, and UKRI have been particularly supportive of the work that we've been doing. So that's EPSRC, Innovate UK and APC. And we're now sitting of the order of 80 engineers, scientists working. It's about 60 Constellium, 15 postdoctoral research fellows, and the balance are IK students. So, in the summary, the innovation portfolios are aligned with the long-term goals. As I say, that doesn't mean that we don't want to understand the science. Actually, that's completely what we need to do to be able to take advantage of that science to be able to use in our product for the future. I've mentioned the UKRI, and that's really important to us. The environment we work in, I think, is relatively unique, where our Constellium engineers work side by side with Professor Fan's academic and postdoctoral research fellows, because we need to develop that technology, that science together. The R&D program, as I say, is a combination of market-driven, but that's basically looking at the science but pulling that science through as fast as possible, and we do that because we've got industrial scale equipment to do that. We have on-campus engineering apprentice program, so we've actually developed an apprentice program now at Brunel where we bring in our apprentices in, they go to the local college, and then when they qualify, they're actually working and running our equipment. So that's the industrial case. It's now it's going to be 21 by the end of this year. And I think really critically, metallurgy represents the cornerstone of our innovation programs. It's about our alloys It's about how we utilise those alloys in the best possible way to lightweight our material, but also for that material to be structurally compliant in what is an ever-increasing and demanding industry. But it's exciting for us to do that, and I think it's really exciting for the people coming into the company to do that as well. So, thank you.
Thank you, Martin, for another excellent talk. I wonder what you're up to with your extrusion press. And you've left your time just for one short question, I think.
Okay.
And gone up somewhere there.
Hello, I'm Sajjad from Alloy. Thank you, Martin. Fantastic talk. I can see that Constellium is heavily investigating and developing new alloys. And I assume that when you come up with new composition, if that is within a spec, OEMs are happy to use those new alloys. But when you have a new alloy or new product out of a spec, it might be challenging for them to accept those new alloys. How do you deal with this situation?
Yeah, no, good question. That's exactly why we have the Circonel program established, and that is why we've got BMW as the main OEM. So they understand when we define the program, it's very clear at the start of such a program. We're not just going to work inside the current compositions. We're going to take those compositions to the maximum and actually understand what's the maximum that can be tolerated, whether it be iron, zinc, whatever it is. And we will work with them to prove that ourselves, and then once that information is available, they will then get the samples, the structures themselves, for them to test. So that what we're trying to do is to bring them with us as we go down that journey.